Okay, everybody, we're going to go ahead and get started. First of all, I'd like to thank everybody for joining this evening for our short talk. This talk is going to cover river ice processes and some of the other processes that govern river ice formation, breakup, and we'll also talk a little bit about ice jams. And we hopefully, upon the success of this webinar, plan to do several other webinars over the next coming months and over the next year or two. So look forward to additional messages from us here at the Weather Service for additional talks coming up. Nothing on the books yet, but we will be planning some other ones. So again, thank you for joining us. The talk's going to last about 30 minutes or so it shouldn't take too much of your time, but hopefully you'll be able to get a few good little pointers on some of the things we'll be talking about tonight. Just very quickly on some background from me, my name is John Goff. I'm a lead forecaster or senior forecaster here at the Weather Service in Burlington, Vermont. I've been here about 15 years or so. Got my start in the Weather Service down in North Carolina and Texas before that. And so if you detect a slight twinge of a southern accent, I'm kind of from the Midwest and South originally. Went to school in the Midwest and also at North Carolina State. So that's enough about me. Let's go ahead and we'll go ahead and move on and just talk a little bit about the rules of engagement of the presentation tonight. As many of you have already found out, all your phones are muted. With this many people on board tonight, approximately 50 to 60 folks. We can't have everybody's phone unmuted because there's always going to be an inevitable audio interference with that. So the conversations will be pretty much limited from me to you. Now, I have responded to a couple of your questions online just briefly, and what I'll try to do at the end of the presentation, if any of you do have questions, feel free to type them in your chat window, and I will try to get a few of those answered at the end of our conversations, into the presentation here, and hopefully provide some insight to that. If not, you can always email our webmaster on our webpage at www.weather.gov/Burlington, and we'll certainly get back with you on that. But due to the sake of time and everything, we'll have to kind of move it along. Also, the presentation is being recorded, and the main reason I'm recording it is so we can rebroadcast to our other users who don't have a chance to join tonight, and we'll be doing that via YouTube and on our webpage as well in the coming week or so. So there'll be an opportunity to review the presentation after the fact for those folks. And again, like we had put out earlier, about 30 minutes on the talk here. I've got about 25 slides or so it shouldn't take too much of your time. Again, so hopefully we'll get you on your way into your evening. So with that, let's go ahead and move ahead and we'll get started. Just a brief overview about what we'll be talking about this evening. Basically, we'll talk about the freeze-up conditions as we start into the mid and late winter, or I should say early to midwinter, and talk a little bit about freeze-up ice jams that come along with that. Then we'll move on to the late winter and spring ice breakup, and some of the threats that go along with breakup ice, such as breakup ice jams. And then we'll talk a little bit about the National Weather Service ice jam warning operations, how we deal with ice jams, how we forecast them, and some rules of thumb that we use as meteorologists to help convey the message that an ice breakup is coming and we may want to look out for ice jams and other threats. So first, let's talk about the freeze-up. In terms of river ice formation, it all starts with, and then the title slide says here, with Frazil. And what I mean by that is it's called, Frazil is a certain type of slushy ice that you'll see forming on the rivers when the rivers get very cold in the late fall and the early part of the winter. I've got some pictures here that'll follow in a minute that'll show you what it looks like. It develops in turbulent, supercooled water that is exposed to very cold air temperatures. Now, what I mean by supercooled water is that the water temperature itself may actually be at or slightly below freezing. So the river temperature may be actually 30 degrees, but what you have to take in mind is that water is very turbulent. And as many of you know, obviously, water that's still will freeze up much quicker than that. It's these mechanical mixing processes in a river that keep it a little bit more open in the late fall and early winter as opposed to a pond or a lake, which will freeze over much quicker. So it's that supercooled water in turbulent air that's exposed to the very cold temperatures. That's when this Frazil ice forms. And airborne ice crystals, whether that's snow or just very minute ice crystals in the cold air, become entrained by mixing into this turbulent river flow, and they see the formation of this Frazil ice in the river. And Frazil ice is a very sticky kind of pancake ice. It sticks to itself and everything else. It can stick to rocks on the river bottom. itself and in parts of the bank, and that's how it generally forms. So as you look at some pictures here on the left, you see a gentleman's hand holding some of the Frazil ice. It almost looks like ice out of a snow cone, so to speak. It has that kind of texture. And as you see on the right here, it forms these kind of pancake, slushy type structures. And I'm sure many of you, when you've been driving over a bridge in the late fall and early winter, seen some of sort of these type of structures moving down the river in the flow. And what happens is it slowly aggregates together and sticks to different things. It piles up in slower parts of the river where the river may go around a bend, things of that nature. I mentioned anchor ice. This is a picture of some ice that's actually sticking to rocks on the bottom of the stream or river. You can see these white kind of pancake structures as you see under here, and I'll kind of illustrate here really quick. You can see like a structure here and here. This is called anchor ice, and I'll touch on that a little bit because they're important in the formation of certain other things during freeze-up, like freeze-up jams. Let me get back to here. Okay. So this is a picture as the Frazil ice is continuing to stick together, a picture of a river bend. So as you can see in the slower part of the river bend, where I've labeled here, the Frazil ice is collecting where the river slows down on the outside of the river bend, and where the current is still faster on the inside of the river bend, it's still open. You can see the river steaming, and it's through this process that the ice is slowly built up and thickens and freezes and hardens. So that's kind of the general process by which a river freezes up in the wintertime. Again, this can happen during a range of months, generally in the North Country here, December through about mid-January, and that's a range of dates depending on how early the cold sets in or how late it sets in. Some years this can happen as late as early January on some years. Most years it's in December. And so this is the final kind of end all here. After the river is completely frozen up, that Frazil ice is locked into place. There may be some anchor ice underneath there, and snow has started to fall on top of it. You can actually see, and I'll show you right here, some rougher parts in the river where maybe this was the last part to freeze here, and this area out here was a more stable flow that froze up earlier. You can kind of see some of these textures in the ice. I'm not exactly sure on this particular picture, but that's what I would surmise on a picture like this. Okay, so when we freeze up in the winter, there are some minor things to consider in terms of ice jams during freeze-up. We call these freeze-up jams. Makes sense because it's when the river is freezing up. They typically form during the initial freeze-up in late December to early January, especially during a really cold Arctic outbreak. The ice grows together and restricts the flow and may force the river out of its banks. These are very stable formations. They often act as focal points for spring breakup jams, and I'll touch on that in a minute. So I showed you that anchor ice earlier. A lot of times, if that anchor ice forms in the bend of a river or in a constricted part of the river, like against a railroad trestle or a bridge abutment, or even where the slope of the river changes, you're going from a steeper slope to a shallower slope, such as, and I'll just kind of draw it on the screen here really quick. If you have a river channel that's really steep like that and then it levels out, the current is going fast here and then slowing down, you can get anchor ice and jams to form like in these locations here, something like that. So those are also places where you can form freeze-up jams during those situations. So what are some of the predictors we use for freeze-up jams? One of the rules we use here in the Weather Service, and a common kind of old wives' tale rule of thumb we use here, is 3 consecutive days with daily average temperatures less than 0. Now you think of that, that's pretty cold. This is daily average temperature. This is not the high or the low. This is if I take the high temperature and the low temperature and take the average. If that's below 0 for 3 days, then that's a good predictor for freezing up and maybe freeze-up jam predictions. So that's one rule of thumb we tend to like to use here. Another thing is talking about freeze-up jam mitigation. So what kind of things can we do if we notice a freeze-up jam? What can we do to mitigate any kind of impacts from that? There's a number of a variety of things you can do. Some of the main ones I've listed here. You can release warmer water from a hydro project upstream if that happens to be the case. That's not always the case in a lot of these situations. But in some cases, if you have a dam upstream or some sort of hydro operation, the warmer flows coming out of that can help melt some of the water. You can also dig a channel to release the water. I believe this is a picture from maybe about 10 years ago up in the Hardwick area, I believe, or Walcott, somewhere up there on the Lamoille River. You can actually do something as simple as get a backhoe out there and dig a channel through there. Or you can do nothing. A lot of times these jams form in place in rural areas where nothing is really affected, and maybe bottomlands or some rural fields, and it's not really impacting human structures in a sense, and you kind of just let it go. Water is going to find a way around it. So those are some of the, in terms of freeze-up jams, some things that you can do to mitigate these type of things. And we work as the Weather Service in close coordination with our emergency management partners and others, public utilities and things of that nature, when we have these ice jams, to coordinate with them on what may be happening on the river flows. Okay, let's move on and talk about the spring thaw, because this is probably a little bit more important when you look at the spring breakup after a long cold winter, certainly like we're having this winter, and you do starting to deal with breakup ice and ice jam potential. This is where you have to be a little more concerned because you have a lot of volume of ice, and you're also melting a lot of snow in the mountains, so your river flows are going to increase a lot. So this is going to get a slight bit more technical, but just bear with me, I'll try to explain things. So you have a slow ice melt in the spring. As we get into March and April, the sun angle is getting higher and higher, and it's really a law of diminishing returns. The direct sunshine on the ice with a higher sun angle and the increased solar radiation is by far takes the greatest toll on the ice cover. It's not warmer temperatures, and in most cases it's not really high river flows due to rain or snow melt. Sometimes that can be the case, but in most general conditions we're not getting widespread flooding in Vermont most years. It's this direct sunshine as the sun angle gets higher. It breaks down the ice crystal bond. The ice turns gray. It starts to rot, as you can see in the picture here. You start to open up some channels in the ice, and water starts to find its way through. And again, the warmer spring flows that are a little bit higher, that often helps as well. But in general, it's the direct sunshine is the major player on rotting the ice away. So in terms of ice breakup, we use some rules of thumb here. One of the most simple ones we use at the Weather Service here, and other offices use it, Weather Service offices use it as well, is you want your river rise, meaning the number of inches or feet on the river with the spring flows increasing, to be at least 2 to 3 times the river ice thickness. Okay, so I've included kind of a general plot down in the below in this image here to show you just a general river rise on how it would rise. In this case, it's rising above a record stage. But the point I wanted to illustrate here is just what a river rise may do. For example, if I have ice thickness of 12 inches, I need 36 inches to, in general, be concerned about that ice breakup. Because when ice is thick like that, and even in thinner ice, it's very elastic. It tends to bow up and bow down and not just crack apart. It's not as brittle as people think. So there's a lot of give and take with the ice on the flows throughout the winter and into the early part of the spring until you get a really good river rise, and that tends to start to break it up. So if I have a 12-inch thick ice cover, then you need a 2 to 3 foot rise for potential breakup, for the breakup stuff. So those are the kind of things we look at. That's one good rule of thumb that we use. This one is a little more complex, and I'll go through it with you. It's called thawing degree hours. And the first rule of thumb we use is we generally look at a number of thawing degree hours about 300 for thick ice cover and somewhere around 200 for thinner ice cover with rain and snow melt. We need a 12-hour minimum thaw and preferably over 40 degrees for at least 6 hours. And honestly, of the years I've been forecasting, I'd like to see 40 degrees for at least a day or two. And then that starts to get me thinking about the breakup. Alternatively, some other rules of thumb that are out there, you need an average daily temperature of about 42 degrees and ice thicknesses of at least a foot. I know the Weather Service out in, I believe, Buffalo uses that rule more commonly. So what's a thawing degree hour from what I'm talking about? Well, basically a thawing degree hour is the difference between the temperature observed at the top of the hour, between that and the freezing degree mark. Okay, so if I have in the left-hand column here on the top, I have an hourly temperature of 38 degrees. That's 6 thawing degree hours. It's 6 degrees above freezing. The next hour I'm at 39, so I get 7 thawing degree hours, during that hour, and so on and so forth. and you're summing these thawing degree hours over a period of time, over a day, over 2 days, over 3 days. Okay, so I just listed a standard 6-hour little period here, and you can see I got 49 thawing degree hours after that 6-hour period. And if you recall back on the earlier slide, we're looking for about 300. So on a fairly decent thaw, you can see how this adds up pretty quick. You don't want temperatures to rise too quick. You actually like a slower thaw. You don't want to see temperatures in the 50s for a day straight, because that could really start to cause some problems. Another way to look at it is through a graphical interface, and I'll try to illustrate here. I've got a red line and a blue line, okay, and I just basically made a kind of a dummy spreadsheet and added a bunch of thawing degree hours for a 24-hour period. And let me use my cursor here to highlight. So I've got a 24-hour degree period down here on the bottom, okay? And the thawing degree hours are increasing on this red line here as I go up. Okay, so I can't remember the temperatures I put in here, but it's above freezing. So they're adding up. I'm sorry. Take that back. These are the temperatures. Sorry. These are the temperatures. So you can see them upper 30s through the mid 40s, back down into the upper 30s toward the end of the 24-hour period. Okay? So we're summing up all these thawing degree hours, and then that's what you see on the red line, these thawing degree hours increasing. And so by the end of this 24-hour period, in this given scenario, it's continually increasing, and I'm up about 80 thawing degree hours in that case. Again, we're looking for, on a decent ice breakup, about 300 thawing degree hours, 200 if the ice is thinner. On a winter like this, where we've been really cold, ice thicknesses, some of the data I've recently looked at, 1 foot to 1.5 foot thick on the rivers. So in lieu of the sun just rotting that ice away and nothing happening with just average melting conditions, if we had a big rain event and you have a lot of snow melt running off and you're thinking about ice breakup on a winter like this, you're going to want to lean toward that 300 thawing degree hour type of situation. And you'd have to see the time period on when that may occur, and that's when you may see us issue flood watches and things like that for potential river ice breakup. Okay, so let's talk about breakup ice jams. Breakup ice jams form when high river flows break up the intact ice cover and they carry it downstream. Well, that's all fine and dandy, but what happens after that? Well, they mainly form where the river and water velocity slow down. I touched on that briefly about the freeze-up jams and where they may form. So very common places, bridge abutments and sandbars in the river where it's shallower. Decreases in channel slope. I showed you that earlier about how if a channel slope is steep and the river's running fast and it kind of comes into a flat area on the bottom of the river, it slows down. Bends in the river or any other natural constriction. So an oxbow in a river, a place where a railroad trestle or bridges cross, where you have the bridge abutments or railroad trestle abutments in the river, places where the ice can jam up. And also the old freeze-up jams. If you have old anchor ice and freeze-up jams from earlier in the winter, those are very stable structures, and a lot of times they're still stuck there come the spring breakup, and that's where the ice can all jam up in and hold up again. So some key points on any ice jam threat, but breakup jams in particular. The primary threat of flooding from the breakup jam is from the backwater behind the jam. Okay? It's not from the jam releasing in this massive tidal wave coming down the river and flooding everybody 20 miles downriver. The truth of the matter is that flood wave attenuates very, very quickly over time. So by the time you even get less than a mile down the river, that's very attenuated out, and it's not as nearly the impacts that you have as opposed to the impounded water behind the jam. So that's one thing to consider. The picture on the right is Montpelier, our probably most famous ice jam in the state over the last 50 years, and that was all from backwater behind an ice jam, not from a flood wave. Again, with these ice jams, these breakup jams, they're very sudden. So from a warning perspective for us, often we don't know they're going to happen a lot of the time. Sometimes we can see river gauges react to an ice jam and ice movement, but we really a lot of times don't know if it's true until we can coordinate with local officials and emergency management. So keep that in mind, that these are not really, we have favored places where ice jams do occur in our area, but it's hard to predict. It's hard to predict exactly if or when it's going to occur. We have a good idea on when the ice may break up, but whether it's going to jam or not, there's still a lot of subjectivity in that. Again, Montpelier 1992 on your right, and again, a lesser threat from the release of water downstream in most cases. This is a very classic and prone place for an ice jam to occur. You kind of have a double whammy here. This is the Lamoille River at East Georgia. Many of you may be listening and have been over the highway here. This is where the Lamoille River empties into Arrowhead Lake up by Georgia and Milton. So two things going on here. You have a lot of ice coming downstream. You've got a bridge going across here with abutments in the bridge slowing the ice down. And you've got Arrowhead Lake to the left side of your picture, not shown, where the water velocity slows down into the lake. So all of this river is flowing into this lake and slowing down and fanning out into the lake. And so the ice really doesn't have anywhere to go. The ice ahead of the other ice upstream is slowing down, and it's just like a traffic jam. It backs up and backs up. If you've ever been to this location in particular, it doesn't affect a lot of people. There used to be some homes affected by these jams around this area, but they've long since mitigated these factors, and most of the local roads around here that could be impacted, there's other ways out of there, and there are no homes threatened. So this is more kind of a gee whiz type of jam, but it is an awesome spectacle. If you've ever been up to this location in certain winters when the ice releases, there are very big blocks of ice that can come down the river here, some up to the size of a small car. So breakup jam mitigation, let's talk about that briefly. Generally, you can do a couple of things. Some of these are very similar to what we talked about in the freeze-up jams, how you deal with them. You can release warmer weather from hydro operations, a power plant, things of that nature to help melt the ice. You can excavate if it's a smaller river. One other option, and that's been used and considered at times, is dusting, either with leaf mulch or other dark type material, often carbon based, that can absorb the sunlight, a dark layer of material on the ice, and it makes it warmer and it helps melt the ice from the top. Those are certain options, and it generally, when you deal with a dusting option, you're dealing with something that may be more high impact, because it can be cost prohibitive to local town budgets by spending the extra cost to do this. So a lot of that is a kind of a weighing out of the scenario on how much am I willing to spend, and is this worth it? On a certain high-end type of situation, I know we had a situation in Montpelier several years ago, not the 1992 event, but maybe 5 years ago, where they had a freeze-up jam and some concerns about flooding. This option was considered as a possible workaround of that. You can also do blasting. In some cases, you can use dynamite, and it's not really a recommended one because you also have a public safety concern to deal about, but you can blow up the ice. And I think I may have a picture of this for you in a minute when they did that up in New York a number of years ago. You can also do nothing. You can have people go out and monitor it, and that's often the case in these situations when they're not sure whether it's going to flood or not. They'll have local officials or state police drive out through the 1 to 2 day period that's of greatest concern and continually monitor that ice jam so that they can get the word out quickly if something starts to move and back up. And we're in close coordination with those officials when those type of situations arise. Be honest with you, 90% of these ice jams a lot of times are pretty much harmless. They don't affect municipal areas. They're out in the country, flood a few fields, maybe some secondary roads. But there's that 10% where you got to be very careful about, and it can be quite dramatic and can be a threat and have an impact to society and threaten people's homes. So you got to be careful. Yeah, here's the picture I was going to show you. I couldn't remember if I was going to put that in. This was the Great Chazy River. I believe it was, I think, late 90s. It was right, I believe, before I got here. I got here in around 2000. And they actually used dynamite to blow up the river ice in this one certain section. And they pulled all the people back, and the ice was blown everywhere. And some of the ice landed pretty close to some of the people. I think there's even we have a movie about showing that situation where the ice is blown up. But again, kind of a last-ditch effort on how to deal with some of these things. But in this case, I guess they chose to do that. Okay, let's move on to National Weather Service hydro operations. I could get as complex or as lengthy on this as possible, but for the sake of brevity, I'm going to go through this fairly briefly, but just kind of illustrate kind of how we deal with some of the things here, especially in terms of the river ice type of issues, not as much flash flooding. We can probably touch on that on a later webinar. So we're responsible for daily river forecasts for major rivers in our area out to 48 hours. We do cover all flash flood warnings, and that can include ice jams. Most ice jams we won't put a flash flood warning out for, which would tone alert on your radio and would have an EAS alert on your television screen with the scrolling text. Excuse me. But on certain high-end situations, like that Montpelier 1992 example and picture I showed you, that would be a situation where you put out a flash flood warning because people's lives are affected. You have very cold water flooding the downtown district. We have daily coordination with our Northeast River Forecast Center, who covers a lot of the river forecast and river modeling in our region. They're based down in Taunton, Massachusetts, just southwest of Boston. We coordinate them daily, and then more critically during times of these river ice breakup scenarios, which will be coming up probably here in the later half of March and into early April, or in any given high-end flash flood event, or certainly an event like Irene when you had big flooding. And this coordination is especially critical during high water episodes. We work very closely with them, and we're not working by ourselves out on our own. We also coordinate with our surrounding offices a lot during these situations. In terms of toward improved ice jam prediction, situational awareness is key. Like I touched on briefly earlier, they're unpredictable by nature. We talked about some of those rules of thumbs I talked about. The river ice breakup thickness factor, remember 2 to 3 times the thickness of the ice to break it up solidly. And some of those thawing degree hour techniques we use. We also have an ice jam database that we locally run in-house that helps our situational awareness monitor existing ice jams, and also to refresh our memories and go through each season, where are the most prone locations of ice jams, where do they occur. I've got a small map up here in the upper right part of the screen with our kind of forecast area on it. I'm not trying to illustrate you to understand where all these little points are. I just wanted to show you there's like little dots and areas on the screen, and we can keep track of where the more favored prone areas for ice jams are. And again, we coordinate closely with local officials during all these processes to make sure we get the message out should that be the case. So in summary, let's go through this really quick. River ice forms through an aggregation of Frazil ice. Remember, that's that pancake sticky ice that kind of sticks to everything. The river bottom, rocks, the river channel, the sides of the river, places where the river slows down or is constricted. And the early winter freeze-up may lead to freeze-up jams after this ice becomes thicker and slows down. In general, and I should have touched on this earlier, the breakup jams are much more of a threat than the freeze-up jams, and the freeze-up jams are not as prevalent. There's not as many of them as the breakup jams, and it kind of makes sense because all the ice is breaking up in the spring. Only certain places would be more susceptible to a freeze-up jam in the early part of the winter. The spring breakup in the March and April time frame up here is due to a variety of factors, most important being the direct sunshine. The higher sun angle, increased solar radiation, it breaks down the ice crystal bonds within the ice and it tends to rot it away. In certain years, if you get a high-end weather event, that may not particularly be the case. You could have rapid river rises and snow melt, and that would overwhelm any solar radiation process and break up the ice. Most years on most rivers, the sunshine takes the greatest toll. And finally, the National Weather Service, we use a variety of tools and rules of thumb to predict and warn for potential ice jams and their threats. We coordinate closely with local officials. We use these rule of thumbs and can see them coming as we're forecasting out in the coming 3, 4, 5, 6, 7 days ahead, and are very cognizant to get the word out when those threats arrive. So with that, that's about all I have. It looks like we were pretty close on time. That took about 25 minutes or so. So let me take a look at some of the questions here and see if I can answer just a few of them here for the sake of time. Let's see. This one is from John. Can ice thickness be roughly calculated with thermal imagery based on temperature differences? That's a very good question. I'm not exactly sure if that's true. We do run aerial overpasses with aircraft from one of our other monitoring centers. It's called the National Operational Hydrological Remote Sensing Center up in Minneapolis. And they do LIDAR gamma ray flight lines each winter that kind of can detect the SWE, the snow depth, the snow liquid water equivalent. So I would imagine there may be some applications to detect the thickness of the river ice. One thing to keep in mind, though, since I'm not an expert, the river ice is much thicker and denser than a snowpack. So I'm not sure how good the LIDAR or the gamma radiation would see through that on the flight lines. But I'll ask around here. That's a very good question to see if they can estimate it. One of the best ways is we get power companies and other observers around the region that estimate river ice for us and can send in anecdotal reports of the general thickness. In general, with our smaller rivers up here and the length of the winter, depending on the winter, and if you have a midwinter thaw and it breaks up and has to reform, John, 6 inches to 18 inches is that range in general. Certainly on a pond or lake, it could get thicker because of the still water. Let's see. This was from Benjamin Weir. Can precipitation affect river ice thickness and structure? It can. If you have warm rain falling on ice cover, it can certainly help melt the ice. When warm water hits on ice and runs down into the ice, it releases heat. It's just a physical process of ice melting. So that can certainly speed up the process. So if you have a solid ice cover, Ben, and you have let's say it's 45 degrees and you have heavy rain falling on that, that can certainly help rock that ice away. But I think in general, outside a large-scale heavy rain event, that would not be the case. Precipitation in general is not long enough. I mean, in the case of something like Antarctica, where the snow piles up for eons, certainly that impacts how that's compacted and increase the ice thickness. But up here, I'm not positive how big of a role that would play. Let's see. Let's move on to a couple more here. Let's see. Are there trends showing, this picture is from Matt Peters, or this question, are there trends showing seasonal shifts in ice jams that may be related to climate change? Not that I'm aware of. Again, you would have to go back a longer period of time than just maybe my experience here in 15 years. I think the shifts in ice jams is probably more related to river channel morphology and how that would change over the years. One thing that could happen, and this is just one thought that came to the top of my mind, Matt, is after Irene, we had some of these huge flows after Tropical Storm Irene, and it actually altered the river channels in some cases and stripped it down to bare bedrock, especially in southern and eastern Vermont. Some of those river channel morphology changes there, I think that could probably play a greater role on where a future ice jam. It may have changed the river channel so much that ice jams now don't form where they used to, and now they form in a different place. As regard to climate change, I would hazard to say that's quite unclear at this point. It's an interesting question, but it would require some research. And let's just get to one more. This is from Bonnie Richardson. Will this presentation be online somewhere? Absolutely, Bonnie. We're recording the presentation, and in the coming days, we're going to put it on our YouTube channel, and it'll be available off our website. So you'll be able to re-listen to it, this entire recording, and that's what we plan to do with all of these presentations as we come through. I'd like us to do one about every month or so if we could. That may take certain efforts, and it may be a little thin in the summer when our staffing isn't as great here. But I think there are a lot of interesting topics to be covered, and I like this 30-minute format so that we won't take up as much of your time, but it's an easy time for us to give it to you, and you can get a little information for it. But to answer your question again, yes, it will be available on our YouTube channel, and you can play it back at your own leisure at that time. So that's all I have tonight, folks. I hope you enjoyed the presentation. Again, I want to thank you for joining us. I hope you picked up maybe just a few tidbits from us. And again, if you have any further questions that I wasn't able to get to tonight, we do have a webmaster email on our webpage at www.weather.gov/Burlington. Feel free to shoot a question or two to those if there's something I didn't get to tonight, and I'll be happy to respond to you in the coming days, and hopefully I can help you out. So again, thanks for joining us, and have a good evening. We hope to see you again sometime in the future with some of our future talks. Good night.